So if you just think about pure geometric effect, the change in material property, which is the change in resistivity, rho, would be 0, right? So let's start with that. Pure, right? Oh, I can't even write here. Pure geometric effect. Zero will be 0. Makes sense, right? So if you calculate gauge factor, in this case, what is it? It will be dr over r over dl over L, which is nothing but the epsilon. What is it? Remember the previous page. Sorry, I just removed it. What is it? Because dr over R consists of 1 plus 2 nu times dr over L plus d rho over rho, where d rho over rho is 0. So you're just left off with 1 plus 2 nu. Please take a look at your previous line of equations. All right. So let me ask you, what is typical number of Poisson ratio? How much change in the lateral contraction will occur if you elongate a material, for instance, like metal? Is there any opinion? Would it be 0.01? Would it be 0.1? Would it be 1? Would it be 10? Obviously 10 doesn't make sense, right? You just elongate by 1, reduce by 10 times. That will be very strange material. 1 is still, strange, right? Just elongate by 1 meter, it'll reduce by 1 meter. Doesn't make sense. 0.01 might be too small. So the typical range, of material will be about 10% or more, so of the contraction, And at the other end, there's even more strange material, which is called metamaterial. Metamaterial, in that case, if you actually elongate such material, instead of getting shrinked, it'll actually inflate. And that's like a magic. And nowadays, a lot of people are actually talking about such metamaterials. Unfortunately, I don't have enough time to cover such topic, but you'll find such topic in the any other class. Okay, so we'll focus on just normal material, not like Harry Potter material. Okay, if you have metamaterial, trust me, you can come up with invisible what is it called, shield. Anyways, so nu typically will be 0.3, a little bit big, sometimes 0.5. These are the typical range of this material. If you just plug in this number, gauge factor, for instance, if you just plug in 0.3, it'll be about 1 plus 0.6 or 1 plus 1. So gauge factor, at a maximum value will be about 2. Okay. So indeed, this is something you learned from solid mechanics course, right? If you remember, you can remember the strain gauge. What is strain gauge? You just have the pattern of resistance with the metal on a surface, so that if the material actually deforms, the pattern will deform this way, and that will be ended up with this much of resistance change per unit amount of change in strain. So we call this strain gauge. So strain gauge effect is not very strong, yet it will give you some kind of a change in the resistance. Sorry. What do we do to increase the strain gauge effect? Well, simple. Just simply have longer material. The longer the material you have, the larger this effect will be. So that's why your strain gauge will look something like this. So to increase the length of the material as much as possible. However, in this case, in our class, we are interested in the use of a different effect that came out of different material. And what is the material that we use? Silicon, right? Group 14 element, the magical material of silicon. So if you look at silicon, we call such effect piezo resistive dominant effect. So this is really true piezo resistive effect. Write down a little bit below. Dominant effect. Okay. And this effect occurs with the use of some new material like semiconductor. Silicon doped with the arsenic, silicon doped with phosphorus, silicon doped with the boron, for example. Then you can come up with p-type material, you can come up with n-type material, and you see that depending upon whether you have a p-type or n-type material, you'll have totally different result of this piezo resistive effect affected by the direction of stress. And that's very, very interesting effect indeed. And what's more interesting, what's more impressive in this case is that gauge factor you can achieve will sky rise. It will go up to at least 80 or even 200. Amazing, right? Amazing number. What was the gauge factor you can achieve with the normal metal or the conductor? There's only 2, right? But in this case, if you use special material like a semiconductor, the gauge factor you can achieve is, look, 80 or 200. It's 2 orders of magnitude bigger than you would obtain with just normal material. So this is really magical effect. Okay. How does the effect occur? Well, again, unfortunately, we don't have enough time to cover the whole thing. So I'm gonna just put everything in a nutshell, small nutshell, So nutshell, So you can really, explain in 3 lines. First of all, there will be a stress applied to this material, and this stress will alters energy level of the major carrier. That's why this is a totally quantum mechanical effect. So this is directional. Depending upon which direction of stress, to which direction stress is applied, this energy level change will be different. Because we are talking about single crystal silicon, even though we'll also talk about polycrystal silicon as well. What is single crystal silicon of group 14 element? It's like a diamond. It's like a carbon in well arranged lattice, face-centered cubic lattice. So again, we don't have enough time to go through this lattice analysis, but it's just like a diamond. It's really nice crystal orientation. So with this, because stress alters energy level, the major carrier density will change. How does it change? It will be redistributed. Redistribution in this case, right? So redistribution of the major carrier will occur. What are the major carriers? Well, if you have a p-type material, for example, how can you create the p-type material? It's like a magic. It's like alchemistry, 연금술, So you have a semiconductor, silicon, and you will do something called doping. You will actually make some impurities diffuse into the single crystal of the silicon. And the impurities could be something like a boron. Boron of uh, group 13 element. Group 13 like aluminum, boron, aluminum, arsenic and other things, So boron, if you just mix with silicon, you have a deficiency of electron. And we call this deficiency of electron a hole. So where, every other place you have filled electrons around, which actually form this, what is it called? The covalent bonding of this single crystal silicon structure. You have a deficiency, which is a void. So this void among the sea of electrons, which is negative, can be thought of as positive. So it's a positive carrier. That's why we call this positive p-type silicon. Again, bear this in mind. If you mix silicon with group 13 element like boron, aluminum, and arsenic, you're going to be ended up with p-type silicon. That's going to be major carrier. And then, on the other hand, if you mix this silicon with group 15 element, like phosphorus, for example, phosphorus in phosphorus plus silicon, you're going to be ended up with n-type silicon. What is the major carrier of n-type silicon? Yes, electrons. Why is it electrons? Well, we have a full of electrons in the first place around the silicon, which forms this covalent bonding. But because phosphorus has one more electron than this electrons needed for the covalent bonding, that provides free electrons. So in that case, you have more electrons. You have a more negative material in there. That's why we call it n-type silicon. Again, bear this in mind. You have a silicon, group 14 element. You mix with group 15 element, like phosphorus. Then you're going to be ended up with n-type material. So you have a p-type material on one hand and n-type material on the other hand. P-type material major carrier are holes, and n-type material major carriers are electrons. So depending upon this major carrier, this redistribution characteristic will become different, which is like a magical phenomenon. Anyways, with this in mind, so eventually what's happening? Well, there will be a change in the material property. And what kind of material property are we talking about? We are talking about resistivity. Rho will change. Resistivity change will occur. And this is really, really, really important.